Greetings. Welcome to our presentation on soils and site work. Topics that we're going to cover include earth material, soil boring logs, earthwork and excavation, geotechnical engineering, and erosion and sedimentation control, also referred to as E&S measures. Soil is the material that you find after topsoil has been removed. Topsoil is the organic soil at the very top of the earth. And here we see a nice cross-section. Horizontal layer O at the top here represents the topsoil that has the plant growth. Below it we see subsoil. Below that, partially weathered bedrock, which would be here, points out on the left that this soil is being formed by the disintegration of rock. So at the very bottom we have the rock, and above it we have rock that is disintegrating, which is partially weathered bedrock. Soils are made up of grains and water and sometimes air, and are classified by size as gravel, sand, silt, or clay. And here we have a visual showing the relative sizes of them, clay being the finest, silt larger, sand larger yet, and gravel the largest. And the same here on the right hand side, we have a visual of the sand particles, very large, silt smaller, and clay very fine. This image shows how engineers classify the soils based on these three components. We have clay at the top, silt at the bottom right, and sand. Many soils are made up of a combination of them, and that's what we see here. So the percentage of silt, the percentage of sand, the percentage of clay, and then we have the mixes of each here. The Unified Soil Classification System we're going to look at next. I'm just going to skip quickly to the next slide. And what it's pointing out here is this, again, this is used by engineers to describe and to classify the different soils that we work with. And it points out that the ones at the top of this list are the ones that are best suited for structural applications. So I'm going to go back a slide. Here, this would be the top of the list with the gravels and the sands, followed by the silts and the clays. And then as we move further down to the more organic soils that are much less suited or not suited at all for foundations. The ones up at the top that are best suited exhibit greater load-bearing capacity. They could support more, greater stability in that they don't change. They have their ability to support structural loads without shifting, or their ability to support without shifting depends primarily on the friction between them to keep the pieces from sliding past one another, and this is referred to as a shear strength. Shear is the force where two things want to push past one another, and the shear strength is the strength that resists it. These soils are referred to as frictional or cohesionless soils. The soils in this classification system are also referred to as being well graded or poorly graded. And here we see an example of a well graded soil. It contains large particles down to small. Uniformly graded does not have that variety. And then this one is called gap graded, where there's a gap. It has the large particles and the small particles, but not the mid-size particles. And here we could see another visual showing the well graded, how the smaller pieces kind of pack in and make more of a solid composition. And here the poorly graded does not. It doesn't have the small particles to do such. And then the gap graded just doesn't have the variety. So soil gradation is an important aspect of soil mechanics, an indicator of other engineering properties, such as, so these are the structural, describing the structural capacity of the soil, how well it resists being compressed, the shear strength that I already referred to, as well as its hydraulic conductivity. Well, now we'll take a look at the individual soil types. So clay is a sticky or cohesive soil. The particles are so fine that there's an attractive force between them holding them together. It's possible to dig vertical walled excavations without temporary support in this type, and that's what we see here. So this is obviously a small, just a step footing, a small, on a small scale, but we can cut sheer horizontal walls in clay without having it collapse. That's what that means. The image on the left describes that. Clay is an expansive soil. This is the image on the right we're talking about now. It's prone to expand and contract as the moisture content changes, and it could be very expansive, increasing in volume by as much as 10%, which is very, very significant. And the result could be causing damage to foundations if not properly accounted for in the design. So here we have the clay soil that expands when it rains, and it pushes on the foundation wall, and horizontal cracks in foundation walls are often a telltale sign of this type of damage, that this type of damage is occurring. Sand. So sand particles are bigger and not so sticky. The particles slide over each other, but they are rough, so the sliding is resisted by friction. Right here we see this points out that slightly wet sand, however, does experience some cohesion. So that's how we make sand castles, for instance. Here, the dramatic effect of moisture on smaller grained soils is something that's called soil liquification. This is basically what happens with quicksand, essentially. So sands and silts basically lose all of their strength and act like liquids when they're subjected to large changes in load. So here, this is pointing out that after an earthquake, this is what occurs, and this is the soil basically loses all of its bearing capacity and just becomes liquid. That's what quicksand is, essentially. Here, so we say in summary, the shear resistance of dry sand is almost entirely a friction and an interlocking of grains. So the shear resistance is pointing out how the sand has this great shear resistance, and it allows it to keep its form, essentially. Finer grained soils have some stickiness and some cohesion, so that the shear resistance depends on friction and on cohesion. Okay, that's a little redundantly written. And this concern is related to both excavation and bearing capacity. So here we see what is referred to as the angle of repose. I'm just going to jump forward one slide and then I'll jump back to that. So here's the angle of repose for different soil types. So in just left to itself, compact clay will allow for a relatively steep angle, and saturated clay, on the other hand, a much more shallow angle, with sand and silts being in between the two. So now going back, you could imagine with how this concerns excavation. Here we see the frictional soil that allows or requires a angle, a shallower angle, and then here with the more cohesive soil, we could cut that sharp edge. The soil allows that to occur and will stay intact safely. So this is a concern for the excavation of foundations. Soil boring logs are created by geotechnical engineers. They are typically the first on the site. Here's a boring rig. They will drill down into the earth a given distance based on the anticipated needs of the foundation and the anticipated soil types and soil conditions. They will bring up earth samples like this in a big linear fashion, and then they will turn that into a log, which is here. And we will look closely at one of those in a moment. This log contains a lot of important information, the different soil types, how they're classified, which is what we just reviewed, the denseness of it, the sampling points where it occurred, the water content, the weight of the soil, and when the drill refused to move any further. often the soil descriptions are subjective, so it's not an exact science. They're based on experience and judgment. And how dense or hard the soil is often based on how quickly the drill could move through the earth. This is a manual boring rig that would only go down a small distance, as opposed obviously to a hydraulic rig. Now let's take a closer look at a boring log. Points out here that the boring log should be plotted on a site plan and looked at in cross-section so that the relationship of the excavation and structure yet to be designed is scaled to the soils and the water table that exist at the site. So the next few slides we're just going to continue to look at this image and discuss the parts of it. So first we point out that the date is of course provided. Up here at the top we have the date. Points out that the water table could fluctuate seasonally, so that's important to know when it actually did occur. And the boring log number, so in this case it's B1, so there at the very top you see B1. So depending on the size of the site, it could be a handful of boring logs, or it could be dozens of boring logs. So identifying each one by name or number is important, and then showing where that log corresponds to the site plan is of course very important, because over a large site obviously conditions could vary. Here the ground elevation at the boring is given. So the ground elevation is the here, so the elevation at which it is started, so that's ground level, essentially ground elevation at where we started the boring. The drill used was a hollow stem auger. That's identified here as well, the method of drilling. So that for this particular drilling just means that the ground was not rock, so an auger is like a carpenter's auger, so not intended to penetrate rock, so it was a softer material than that, obviously. The soil is logged and classified by depth from the ground surface, so we move from the ground surface down. Here we are at 0, standing on the earth, and then this is in feet moving down, so we've penetrated 5 feet, 10 feet, 15 feet here. The blows per foot is the number of times that a 140-pound drive weight is dropped 30 inches, how many times that has to occur for the boring to penetrate 1 foot. So we drop the 140-pound weight a distance of 30 inches, so that's just a standard in the business, and then we push down 1 foot, and then we measure how many times it takes for that to occur. So it's a description of the density, obviously. The 37 blows per foot confirms the description of a dense or well-compacted soil, and that's here. We see that. Okay, the moisture content is here next to that, and we see how that varies, how it increases and then decreases, so it tells us how dry the soil is. The dry density, so that's a weight, is next to that here. That's the dry density, indicates a well-graded soil. So it will provide a significant cohesion, and that tells the contractor about the friction angle, which we've just discussed. The soil classification descriptions and relative compactions are shown as loose, dense, etc. So that's here in the description. We're talking about dry, dense, etc. Okay, so that was the soil boring log, and now let's talk about the actual process of earthwork. So earthwork are engineering works created through moving or processing parts of the earth's surface, soil and rock. So this includes site work, which is we're concerned about, obviously building, excavation, backfilling, and all other related earthwork activities. Excavation can be classified by the type of material, so this is the type of earth. So we have the topsoil, which we discussed, the earth that follows it, then there's rock. Muck is just useless, basically unsuitable soil that would have to be removed and replaced. or unclassified excavation. So this is a combination of anything. I'll just quickly talk about unclassified. So when a owner puts out a bid, essentially, for contractors to come and do excavation work, they might classify and say, I am looking for a bid for you to remove the topsoil. They have classified that it is topsoil, or they classified that it is rock. But if an owner doesn't know or doesn't want to be specific in fear of maybe of making an error, essentially, they could say that it's unclassified, and whatever materials the contractor comes upon while digging, they are responsible for removing. The benefit to the owner is that an unclassified excavation puts all the risk onto the contractor. However, when a contractor takes on such risk, of course, they charge for it. They don't know if it's going to be an easy excavation or if they're going to come across rock. So they have to kind of plan for the worst case scenario while, of course, producing a competitive bid, a competitive fit. All right, excavation. So contractors rely on these boring logs. So the geotechnical engineers are the first on the site. They produce the boring logs, and the boring logs are provided by the owner to the contractors that would be bidding on the excavation work. So the boring logs provide, as we just went through, the type of the soil. They could gather from that the required slope, so the angle of repose, so the contractors could determine how large of an excavation area there is based on the angle, and then, of course, based on the composition of the material, the soil material, if any sort of bracing or will be required, and if groundwater might be encountered. Questions that contractors should ask prior to bidding. So what happens with excess excavated material? So material that's not going to be used, who's responsible for that? Is it left on the site, or is the contractor responsible for removing it? Who's responsible for clearing, grubbing, and tree removal? So clearing and grubbing is just taking away all of the vegetation that's on a site. And then back to the important topsoil. Where will that be stockpiled? And who's responsible for utility trenching? That's one of those areas. Does utility trenching belong to the earthwork contractor, or does it belong to the electricians and the plumbers? Important to specify the scope of the contractor's work. So if it's not clear, the contractor has to ask these important questions. Another part of the puzzle that contractors have to be aware of and take into their calculations is the different states of soil. So there's swell and compaction, 3 different states of soil. So bank material is material that's in its natural state, and that's what we see here. So this represents a certain amount of soil, certain amount of water, certain amount of air. So when we just happen upon a site, an undisturbed site, the material that's in the earth is bank material. Once material is excavated and taken out of the earth and placed in trucks, then it is loose material. And once that happens, you know, just kind of intuitively, if you dig a hole in the earth, the amount, the size of the pile of material is going to be larger than the hole, because now a lot more air has entered into the composition. So you would not just simply calculate the volume of the dig. You have to calculate how much that material is going to loosen up, essentially, once it's excavated. And all different types of soil have a different percentage that they do loosen up and swell. That's called the swell. And then compacted, of course. So when a contractor is backfilling and tamping or compacting, it obviously shrinks. The soil will shrink. So again, we don't just calculate the volume of the hole to be filled. The engineers will specify that soil that is backfilled needs to be compacted to a certain degree. So that's another calculation that contractors have to be aware of, and we could see that here. So here, all of the air and all of the water is compressed out of it. So these are three good visuals to explain the three different states that we could find soil in. Topsoil removal, so this is where it typically begins. So this is our uppermost layer of soil, as we said, and it is capable of supporting life, vegetation. So it contains all the nutrients and the organic matter. It's very valuable, essentially. So typically jobs will start if the site does in fact have topsoil that is worthwhile. The first step in the process would be stripping and stockpiling it for later use. Okay, so now just to speak a little bit more about the profession, what they do, are geotechnical engineers. So it's a civil engineering profession. It falls under that big umbrella, and basically they're people dealing with the physical and naturally built environment. Interestingly, it goes back, it's one of the oldest engineering disciplines after military engineering, and it was defined to distinguish it from military engineering. Civil engineering is broken down into many different types of engineering. The ones that we would mostly be concerned with include environmental and geotechnical, I've already mentioned. Structural falls under that as well. And the others, not surveying, yes, but the others not as much for building. General civil engineers, not one of these specialties, the more in a broader sense, the civil engineer, they work with surveyors and the others to fit and serve fixed projects in a given site, in a given community, a given terrain. So the things that they design and care about are the grading of the site, the drainage, adding pavement to it, the water supply, sewer service, and utilities, sewer, electric, and other communications. So all of this falls under the umbrella of the civil engineer and the specialties that make up civil engineering. So a tool that the geotechnical engineers create, we just referred to or just discussed the soil boring logs, and bigger picture, they create a geotechnical report. So the soil boring logs would fall within this. Other things that we find are just text describing site conditions, recommendations for how to deal with the conditions that were found, and there are the logs, maps to go across, maps to accompany them, and any test results that came later. So used to communicate those site conditions to the design and construction professionals. So the contractor would look at this to understand the scope of what they're being asked to bid on, and the design professionals would look at this to design the foundations and the structure. And here it provides information on, again, soil, rock, and water conditions in detail. Okay, so I just want to take a look at some of the information that might be found in there, the visual information. So reading topography or topographical maps. So here we have two drawings basically that are kind of meeting each other right at this line right here. Up at the top we have a plan of a site, and below it we have a section through that site. These are the contour lines that describe the slopes of the earth. And what we do to create that section, or to create the section and also to understand it, is we cut a section cut right through that plan, and then each point right here where that section cut was created, we bring it down and we plot it in a section. So there's our first, here's our second, and the intervals, or I should say these contour lines, are laid out at a certain interval. So here we cut and we drop the line. Here we cut and we drop the line. Cut and drop the line, and that's how we create a section through that terrain. And as it points out down here at the bottom, sorry, this is my just repair this screen a little bit here to fit it to the window. So shows the elevation heights of various points on the Earth's surface. That's what I just described. And importantly here, the closeness of the contour lines indicates the steepness or the shallowness of the lines of the land. So here, where these lines are very close, we could see that it's producing a much steeper, or it indicates a much steeper contour, as opposed to here where I was showing it was much more shallow. The lines are further apart, and we end up with a much more shallow contour. Here's a map. Here we could see the contour lines, and they will be provided with an elevation. So here's 1,000 something, I don't know what, if we're dealing with feet or meters or what. So there's 1,000, here's 900, and then at these certain increments they will make a darker line, so it's a little easier to read. And then just by looking at this, we can't necessarily tell if these hills are going up or down, or where's the highest point or the lowest point, but we could definitely tell that there's a very steep area here, and up here at the top, these are more like plateaus. And that information finds its way onto site plans. So that's the civil engineering's contribution to the site plan, and then the architecture and the other engineers, the building engineers, would also provide solar orientation, streets, boundaries, property lines, everything else, and that kind of flushes out our site plan. All right. Now to talk a little bit about earthwork contracting. So, questions that earthwork contractors should be concerned about. So, they want to know the subsurface conditions so that they could produce an accurate estimate of cost and time, and produce a competitive bid, of course. So, questions that they are concerned with: where is their groundwater, and will it need to be pumped out? Most likely it would need to be pumped out, of course. Is there rock? And if so, is it allowed to be blasted, which we see happening here? Or does it need to be ripped by a bulldozer because blasting's not needed or not allowed? And then in general, what's the most effective way to excavate the site? Is there enough space on the job site to store backfill materials? So we take out the materials, then we take out the earth materials, then we build the structure, and then we need to backfill. Is there room? Large sites usually do have such room, but tighter urban sites, obviously not. Can native material be used as backfill? So the material that was taken out, can it be put back in? Or does it need to be processed or mixed with other? So screened, meaning taking things that we don't want in it out, or does it need to be crushed? And does backfill need to be brought in and imported? All right, and then going back, we've already discussed the angle of repose. So after understanding the soil types, then how much space needs to be provided for these banks? Are there any obstructions we should expect to run into? And then when comes time to compact it, what type of equipment would be needed for that as well? And then finally, the shoring, the temporary shoring. So that's providing temporary support to push back the earth while we build. So here we see what appears to be a pretty tight job site. So right here is the shoring, and this is just temporary. So it's quite an effort, as you can see. These columns need to be pushed into the earth, and then this sheathing will be put in behind it, and then they're building this foundation right up to it. And then when the foundation's complete, the shoring would be removed, and then the backfilling would occur. All right, and then finally onto some sustainability issues. So just broadly, protecting the site is always paramount. So protecting the soil, the wetlands, natural stormwater patterns, protecting trees, complying with local laws, stockpiling and reusing of topsoil, of course, protecting against erosion and sedimentation. That's what we're going to look at next. Minimizing, not making the footprint of the construction and the roads any greater than it needs to be, not disturbing the site any more than we need to. How much pollution your machinery is causing, reusing the surplus excavation, what's its next life going to be, how to get rid of waste, can it be recycled, and as I said, disturbing the site as little as possible. So these are all kind of sustainability issues that a contractor would be concerned with. And now I want to specifically talk about the erosion and sedimentation measures. So a sediment control is a practice or device that's put in place to keep eroded soils on a construction site. So we don't want the soils or anything from the site spilling over onto adjacent properties. So that's a sedimentation control, so that it does not wash off or cause water pollution in nearby water bodies. They are typically accompanied and put together with erosion controls, which, as it sounds, these things are designed to prevent erosion. So the less erosion that occurs, the less sedimentation that occurs. Typically, these are temporary measures that the earthwork contractors would put in place, and then when their work is done, they would typically leave them behind until construction is finished. So just to get a visual on what some of these are, very commonly we see silt fences. That's here. Keep the sedimentation from pushing over into adjacent properties. So the civil engineers would specify these in their drawings. There typically be at least one sheet just related to erosion and sedimentation controls, or as I said, E&S measures. So specified by the civil engineer and put in place by the earthwork contractor. Here we do see the silt fences running across the top, and then coming down below we have erosion control blankets. Can't see them too easily in the photograph, but it's essentially burlap that's been tied down to the earth, anchored down to the earth to keep the earth from eroding. And then at the bottom we have these straw wattles that prevent any erosion that does occur from getting onto the roadway and being pulled by the trucks into adjacent sites or onto the roadways. So here now, we're almost complete here. We're just going to look at a couple of images, kind of the hall of shame of poor practices. So this is a red flag. We should not have soil and water pouring off of the job site across the sidewalk and into the gutter. This will find its way back into a storm drain, most likely. So that's what's happened here, obviously, and now it's taking trash with it. And again, fences that are down, fences that have just been consumed by the earth. So ending on with a couple poor practices, or practices that were not executed properly and maintained properly. All right, so that is the end of this presentation. I hope you enjoyed it. Thank you.